Yeah, okay, so this is part two of the series that we're doing on emergence. And in this week, essentially, it was mainly a look at the properties of the material that you get when you mix cornstarch with water, and how basically that can act as either a liquid or a solid, depending on the loads that were on it. Now, the course really isn't going into much detail on the math. A lot of the courses on Coursera won't, because they're sort of introductory and you want to keep them sort of open to the audience. But the basic point of view that they wanted to get across is it may not be the case that the labels of solid, liquid, and gas are descriptive fundamentally of types of things as they are descriptive of how types of things behave in certain types of environments.
That's a perfect introduction because one of the things that I seem to have noticed from this course is that the right answer is the reductionist answer. So they go through, for example, this thing about sand and how if you look microscopically, sand is definitively a solid. But if you look macroscopically, it kind of acts like a liquid. I mean, it flows. You can pour it. It'll take the shape of its container, blah, blah, blah. But then it has a quiz. And the question is sort of, what is sand? And the right answer is solid. So I'm curious about that. It seems as though, even though they seem, at least thus far in these two lectures, to be either presenting an incompatibilist view or perhaps trying to have the audience come to a compatibilist view or a pragmatic view. Nonetheless, when it's down to the bones of people getting credit for the course, the correct answer is solid for sand, and that is a reductionist view of sand. I thought that was interesting. Just like the correct answer for shaving cream is fluid. So even in this course, they seem to be favoring the reductionist view. Is that because we're not good enough at math, or what's going on?
I think that's problematic, and I had a few issues with some of the lectures. I really didn't like the way they were talking about energy and entropy, and I can't imagine anyone would understand what they were saying from the way they presented it, unless they had studied it in chemistry and physics, and you could sort of pick it out. But one of the things that's very difficult in these courses is that you don't know the audience. So you have no idea who you're teaching to. Like generally when you teach a course, you get a feel as you start to speak about the capacity of the audience, and you sort of tailor to this. There's no feedback here, right? So why do these courses sort of throw out hooks to try to get people interested? I think if you say what is sand, and you have to answer solid, I think that misses the entire point. The point should be that it doesn't make any sense to say what is something without describing the environment, because if you live in a really dry area, for example, with high winds, sand behaves like a gas. It doesn't behave like a liquid. It doesn't behave like a solid. It will fill the shape of a container. It is in motion, because it's basically sand is picked up in the air, and that's what it behaves like. As the energy sort of dies down, well, then it starts to behave more liquid-y like when you get sort of sand dunes. Individual collective particles can behave like solids, and I think that's what I would sort of want people to try to understand, that you can't say, is it X, Y, or Z? You need to say, in given conditions with sufficient amount of material, what does it behave like?
So I would ask, I understand where you're coming from. However, would you agree, first of all, that microscopically sand is a solid? And that would hold regardless of environment. So maybe that is the preferred definition that we ought to use. What do you think of
Even
that?
even on an individual level, like okay, like for example, what would you call one molecule of oxygen? Would you call it a liquid, a gas, or a solid? One molecule.
I
That seems to be problematic, right?
Yeah. Yes, very much so.
Right,
Hmm.
because you don't really think about it, right? Okay, well, think about one particle of sand. Think about one particle of sand in sort of a high wind container. So you have a container like a box. There's one particle in it, but there's a lot of wind. Well, that one particle moves around bunches from. If you look at the equations for what that does, you have the equations for a gas. It induces a pressure on the sides of the box. That piece of sand is no really different than anything else. If there is something moving it around, now of course
Mm.
once you put wind in there to move around, you have the wind itself as a gas, so sand becomes part of that. But you could move it like if you charged it and you put an electromagnetic field in there, you could get it to bang around so it would behave like a gas, even if there's no other gas that's in there.
Interesting.
And I
So
think that's
maybe well, that's
yeah,
what they're going to be getting at. Maybe that's what they're hinting at. Is that one of the things that they were talking about is, sort of, do we have a general law or don't we? Right? And maybe if there is only one general law and we can find it, and is it even preferable that all matter behaves according to general laws? Maybe a better general law, maybe the best one, should be about how much things interfere with one another. And that sort of hints at the environmental
wow,
thing that you're getting at.
that's really amazing that you said that.
Well, they said that. I'm just
Oh,
saying
jeez.
that was in the Corsica lecture.
Yeah. No, but what you just said, right? You said maybe if there's one general law, maybe it has to do with the way that things interfere with each other, right?
Right.
Okay.
That was what they hinted
Right.
at
Okay.
the end there. Yeah.
Right. Okay. So when people started learning, the things they studied was very simple models, and they're just called cellular automata models. So you just imagine like sort of this little block, and the only properties that this block has are related to the number of blocks around it. So you could make a rule, for example, if a block has one block around it, it gets really lonely, so it dies. If a block has four blocks around it, well, it gets really overstressed because there's too many blocks around it and it dies. But if a block has like two blocks around it, well, then it lives and basically it will reproduce and make another block. And you can think about how these patterns would simply relate and change over time, right? And there was a bunch of people looking at this and trying to figure out, like, how do you sort of, what kind of laws would sort of predict, because some of these things turn into wild structures. Like you draw like a series of blocks and give it a few laws, and after a few iterations, you have something that looks like a gun sort of firing bullets across the screen, which is a really weird thing. If you think about like all these little machines start coming into play, and you'll see like things moving around like it's wonderful things. And there was this guy, one of the first real pieces of science that came out of it, was there was this guy who worked out that, well, you could actually characterize this by the sort of the interdependence or the sort of interference these things had with each other. And he came up with a way to do it, and it's called a lambda. And you calculate this thing called lambda, and it represents sort of the interference that's in these laws, how these things relate to one another. And the nature of that thing shows that will you get complexity over time? Will you get something that looks like something structural is coming out of it, or does nothing sort of happen? And it's the interdependence that's necessary in a lot of these things. You have to have some way for these things to interact with each other on a group level. That's essentially where the physics is right now.
Well,
It's just interesting as all get out. I mean, so in the Corsica thing, the thing that they mentioned at the tail end was that they were talking about sand. Sand is a solid, but it acts like a liquid, blah, 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 right? And then they were like, well, let's talk about freezing. Nothing really happens to sand unless you really, really, really freeze it. However, if I just tap on this tube, suddenly it's as if the sand was frozen. And that's where they started to introduce or hint at this idea that maybe the general principle should be better understood based on how much things get in the way of one another. And that's where it ended. So I guess it was kind of ending on a cliffhanger. Maybe there's more to this course than I want to give it, at least now.
yeah, and that actually kind of ties back into kind of the higher level effects affecting the lower level effects too, because I think that if you tapped the side of a bottle with two different types of sand, so one was Saharan beach sand and the other one was sand from the bottom of a lake, they would actually interact slightly differently. The Saharan sand would actually be slightly more rounded, so the sand particles on the top would actually move quite a bit more because the fact that they're more like marbles than actual broken glass when you zoom in on them. But one thing I wanted to mention actually that this course actually talked about is property over energy. So when you actually examine the properties of certain configurations of matter like foam, it differs based on energy. So foam is actually a very high energy state. It would actually much rather if all of the gas bubbles popped and the liquid kind of fell down to the bottom of the container rather than it being in this suspension. So it's so I think that I hope that that's something that they'll continue to talk about more is what does the energy of a system do to affect the properties of the system at a higher scale?
Yeah, what did you guys think about them likening the entropy energy relation to, you sitting around your room playing video games?
I thought it's pretty weak.
I wasn't sure that that was a good idea. I don't know. I think that that can bring in a lot of mistakes.
Confusion. I agree.
Yeah, confusion, especially with respect to intent, right?
Right. Because
But
yeah,
I guess
they had to
they
put
didn't have the great community, the great debate community in mind when they.
yeah. Exactly. Yeah, they had to put a concept of like an agent to try to explain entropy, and that's kind of the exact backwards way of doing that.
Well, the thing about some of these concepts is that, especially in thermodynamics, um, they're defined in a very rigorous mathematical way. So entropy, for example, is the heat change at a given temperature for a reversible process. That has a very rigorous mathematical definition, and it does very wonderful things in formulas because it allows you to calculate, for example, whether or not a given chemical equation will happen spontaneously or not. Because given the second law, in general, when things produce a positive entropy change in the universe, they tend to be spontaneous most of the time. The second law is not absolute, and it's a probabilistic law. Boltzmann was the first one to sort of discover that. So
Will
it's
you
very
say that
tractable.
again? What is spontaneous? I'm kind of surprised. I just want you to repeat the sentence again.
Any event will be spontaneous if it produces a net increase in entropy of the universe. And mathematically, it's very elegant to talk about these things. And a lot of the thermochemical um, quantities are defined because they're very easy to work with, like their state functions, for example. Um,
So is this tying in with that video that you posted on the event page?
yeah, there's a number
Oh
of
God,
things.
that was an excellent video.
Right.
Go into that a little bit. Just summarize the first part, right? Because there's two speakers.
Yeah. There's a bunch of them, but
Hmm.
the problem with like when you're saying like how to introduce entropy, it's if someone has a mathematical background, it's very easy because you just write down what the entropy equation is, and they understand what a reversible process is. So it makes a lot of sense, and then you can show how that works in equations, and it has very straightforward applications. But if someone doesn't know any of that, then how do you explain what heat exchange in a reversible process is? And so you end up with something like, well, entropy is like sort of disorder. So like if you let go of, say for example, you have a deck of cards, and it's all like, from ace to king or whatever, and all the suits. If you just sort of drop it, what do you end up with? I don't know, they just like scatter all over the place, right? You say, yeah, so that's like disorder. That's sort of what entropy is. It's like a measure of disorder, and stuff tends to go towards disorder. And people are like, oh yeah, okay, I sort of understand what you're talking about now. And that's sort of how it's introduced. Now, that doesn't really lend itself to any kind of rigorous calculations, but it sort of gives people a hook for sort of what you're talking about.
When
Um,
I think back on like high school, when they talked about sort of entropy on a high school level, I remember them talking about you want to find the entropy is the lowest possible energy. And so there wasn't this thing about disorder, but I'm hearing disorder all the time in this great community, right? This great debate community. Everyone is always talking about disorder. And that to me seems weird. But the idea that, low energy is easier for me as a non-mathematician to wrap my head around. Sort of the lowest energy state would be the most entropy. Is that also a bad way to think about it? And if so, what's missing? Why is there this this desire to explain things using order versus disorder, and is it necessary?
Well, okay, that's sort of a different law. Like, there's four basic laws of thermodynamics, and there's one of them that basically says that zero. They either define a thing or define how it's related to something else. So one of the laws says that zero entropy is at absolute zero, right? But you can never get to absolute zero. But absolute zero would be a minimum
Yeah,
energy
absolute
state.
zero is when nothing is moving at all, not even
Yeah.
jiggling even a little.
Temperature is zero, right? So but it defines a starting point,
Okay.
which is what you need in order to get a scale.
But
Now the
is it really merely theoretical? Because I can't imagine it actually being real. This absolute zero business, this 0 degrees, where nothing is jiggling at all.
Right, because there's the quantum, what's it called? Not free energy. That's a thermodynamic concept. I think it's called the free energy, right? Where
quantum vacuum energy, yeah.
Right,
Yeah,
right,
I'm
exactly.
just I'm
It's
just
the energy
curious.
that keeps the electron from colliding into the nucleus.
Yeah. I'm just curious. I've always thought of that as a theoretical thing, but is it
Right.
really theoretical or
Yeah, so you can go to zero energy. Like, there are some models of the universe in
okay?
which space keeps expanding. If space keeps expanding forever, then space. Now, the thing that's a bit confusing. Okay, when people say space is expanding, okay, so me and you have a distance apart. I don't know where the hell you are. I'm in Newfoundland, but there's some distance between the two of us, right? Now, I could walk in the opposite direction from you, and therefore the distance between us would increase. When people talk about space expanding, that's not what they're talking about. They mean the actual space itself separates. Space itself gets bigger.
Right.
That's what
So
they mean when they say space expands.
can you
So if
relate this space expanding to just 0 Kelvin?
right, exactly. So
How do you
if
relate
the
those
space,
two?
right, so if say there's a specific amount of energy in the universe, right? Whatever it is, it
Uh-huh.
doesn't matter. Whatever
Okay.
that energy is. Now, if space keeps expanding, right, that energy density is going to tend towards zero because the amount of space will tend towards infinity. So essentially as the energy tends towards zero, you're going to have zero temperature because there's essentially no energy left.
Right.
So in an ever-expanding universe, that's essentially what ends up with. You end up with zero energy. Everything is infinitely far apart from each other. There's no energy anywhere. So,
Sorry, I
but
forgot. It's actually not quantum free energy. It's a 0 point energy. That's what I was thinking about. That's the energy that keeps the electron from crashing into the nucleus.
right,
Yeah, but you just said everything is infinitely far away from one another.
right.
I mean, obviously, to a layperson, that makes no sense. How can
Yeah,
you
it doesn't
have?
make sense to a lot of people, right? A lot of physics doesn't make any sense to
Yeah,
anybody,
because
even
if
including
you
the people
mean
that do it.
if you mean literally infinitely away, how is that even possible?
Yeah, because space is expanding, right? And if it's not going to ever stop expanding, right? If space is continuously expanding, then every object is going to be infinitely far apart from every other object at some point in time in space.
I think it'd be better to say that the limit that it approaches is infinity. Maybe that it never actually inhabits that true value.
Well,
I've
like,
got no problem understanding it with respect to limits, right?
Yeah,
That's
exactly.
okay, but that's not what he's saying.
Right.
He's not talking limits, right? He means literally infinitely away. You've got two things that are literally infinitely away from one another. And that somehow is related to whether or not 0 degrees Kelvin is theoretical or literal.
Well,
Am I
I
right?
mean, there is certain things that you could say are infinitely away or technically not reachable. So there's certain parts on the far edges of the universe where one edge of the universe is actually technically moving faster than the speed of light on the other side of the edge of the universe. So they'll never. So even if you were to shoot a beam of light from that one edge, it will never, ever, ever actually reach the other edge. So even though that's not infinitely far away, it is technically not reachable by the laws of physics.
right, but again, you have to be careful. Like, when it's space essentially that's moving apart. It's not necessarily the object of space
Yes, that's
itself.
what I mean. Yeah. Mm-hmm.
But anyway, yeah. So
This is so amazing. It's hard for me to imagine space space itself literally expanding unless there's something into which it is expanding. And I think that's just because of my lack of experience, right?
Well, and it's
I
only
can't
one
imagine it.
theory among others. I mean, there are different theories. I mean, that's the expansionary theory. There are even some steady state theories that actually do comport with all the evidence that we see. Where right now we would just be in the expansionary state of the steady state, and then soon we'll have more of a collapse. But who knows? Who knows?
Well, I mean, one thing they have to be very careful of is that we say things like, well, that doesn't make any sense to me, or like, that just is completely ridiculous. What we're actually saying is, based on the experiences that we have, that doesn't fit into the pattern of our experiences.
Exactly.
And
Right.
that's all that's saying, right? And that's perfectly reasonable. And I mean, like, for example, we move at certain speeds, right? Like, the fastest a normal person is going to move is at about like 100, about 10 meters per second, right? It's the fastest that a normal person can move under their own power. If you get in like higher vehicles and planes and stuff, you really can't move like a lot faster than that. So everything that we experience is subject to, is a view that you would have at very, very slow speeds. So when people started to look at the physics of very high speed objects, it made no sense, because it said stuff like time slows down, length actually changes, mass
Right.
actually changes, and like, does that
Yeah,
make
this
any
length
sense?
actually changes thing is
Right.
really hard to believe, right? I have to just
Time
take that on
changes.
faith. Like I
Time
am just
changes, right?
like I am like morally opposed to that idea.
Well, the time slowing down one is actually, you can make it more intuitive. Where so instead of having
Sure, time slowing
three,
down is easier, but
yeah,
length
right.
literally changing. My body wants to insist that no, if you got really close to the thing, that would be the right measurement, right? So it's just interesting that, you know, Cook's point. Yes, absolutely. My body
But it's
literally wants to reject these ideas, even though my mind is like, well, I can't reject them.
well, and it's
But
actually interesting because the length changing is actually the exact reason why we are able to detect high energy neutrons coming in from space. Because if there
Shut
wasn't any,
up.
yeah, if there wasn't any length contraction, they would actually decay in the upper atmosphere. But because there is length contraction, the atmosphere literally contracts in their point of view, and they can pass through it to hit our detectors.
what has to be very clear, right? Is these are not like people, when people are introduced that, they think, oh, it's perceived, right? Like, you mean if I go to a concert and I really like the band, I just show up and all of a sudden the concert's over. Like, that's what you're talking about. Like, when you say there's time dilation, that's what you mean, right? And I'm like, no, that's not what I mean.
No.
But no, it's not what you mean. That's
It's a
not what the
real,
physicists mean.
right, it's the
They
exact
don't
same
mean
point.
that, which is just
Right.
right. So the way
But
I
that
can wrap
seems
my head
odd.
around it is by sort of adapting different perspectives and thinking that it's okay to do that. But that is not what you are saying.
No,
You are
time
saying
changes.
something way more important than that.
Right. It's no different than like, you experience time now. The time that you experience is a function of the speed that you are moving, and that's a very weird thing for people to think about, right? But it actually is true. So time slows down when you move. So if you start walking around in a circle and you spend your entire life walking around in a circle, you will live longer than if you sit down. Now, it's not going to be very much longer because you can't actually move very fast,
Yeah,
but
probably
you will live longer. And
probably yada seconds longer.
right, but that's a weird thing to think about, right? But there are particles that actually travel at very, very high speeds. So the time dilation that they see is significant. But even the satellites that orbit the Earth move fast enough that they experience significant time dilation. If you take a clock on Earth and the exact same clock and put it in a satellite, well, once they come down, the clocks are no longer in sync. Because that one, they have everything that you would think that would happen at slower speed happens. They literally would live longer. But that seems really weird. It doesn't matter how weird it seems, it happens.
Well, so here's a really good example of a length contraction where you have time on one axis and then distance on one. So this is only a two-dimensional one, where when you add additional time, basically, or sorry, when you're moving in high distances in fast time, there's kind of this arc. I couldn't quite find it quite well, but this length right here, x prime, is kind of forced because this is the, if I remember correctly, the speed of light. And so the faster the speed of light you go, the more x goes towards x prime, and then the more you move in time and the less you move in distance, actually, when you're slow. And the more distance you move, the less you move in time. So you can be moving at the speed of light, and that means that time is 0. But if you're moving at 0, that means you're moving fully through time.
That's not helping me.
Yeah.
Because speed of light is fixed in my mind.
Right, and that's another interesting.
What do you mean?
Why?
You get to the
Why?
speed of light,
Exactly.
And then I'm like, wait a minute, maybe we're just wrong about the speed of light, right? So
those are all very valid questions. Yeah.
Yeah. All right, but so let's get back to 0 Kelvin. Is it real?
Thank you so much for going back to that. Actually, I wanted to go back to that. So the interesting thing is this wasn't actually part of the Coursera video, but was one of the videos that Cliff posted. And oh gosh, those videos are probably hundreds of times better than this Coursera course. But so one of the things that one of the presenters mentioned is that the second law of thermodynamics is actually not a law. It is simply something that we observe in our local part of the universe. It actually could be true that the second law of thermodynamics is actually completely and perfectly opposite in some other part of the universe to make up for what's happening here in this part of the universe. What are your thoughts?
Yeah, so the second law of thermodynamics has a very unique position in all the laws of physics because it's the only law that's time sensitive.
Mm-hmm.
All the other laws are completely invariant. Like one of the first things that annoys people when they start doing physics is you end up with Helena's favorite quadratic equations. You almost always get two solutions out of these things, and one of them are negative, which makes no sense.
Right.
Because they'll say something like, at what time did this happen, or at what position, and it'll be like -50, which means like what, the ball was underground, or Buddy threw it backwards in time. But the equations are completely time symmetric, so they have to allow for this. The second law equation is not time symmetric. It very specifically gives a direction. It says as time increases, this happens. It is the only law that does that, which makes a lot of people question that it isn't really a law at all. It's just the particular boundary value of our universe that created its behaving like this. And it doesn't. You could have, if our boundary conditions were different, that would be a different law. The hook that
now, just for our viewers, explain what boundary and boundary conditions are.
Boundary constraints on our system are essentially particular points in the system that you know had to behave at certain limits. Like, for example, we have a boundary condition on the past because we know there was a singularity. We can trace it back to, so we know at some point in time, some particular value was constrained to be a certain thing, right? Like
Right.
Each one of us has boundary value conditions because we know when we were born. Right, or a simple problem I could give you with boundary value conditions would be something like you have 100 feet of fence, you have to enclose an area. What shape do you use for the fence if you want to get the maximum area? Well, you have a constraint. Your boundary condition is you have 100 feet of fence. So what shape do you actually use, right? So that's a boundary condition.
Right.
Yeah, so that's a boundary condition, right?
Mm-hmm.
So Alex Rosenberg makes the argument. He says, well, like, look, and he's talking about natural selection, and he says, like, well, the only law in physics that could govern this process has to be the second law because it's the only one that's time sensitive.
Exactly.
And the view of evolution is a time sensitive thing. It happens going forward. And he makes this very interesting argument. He has the video that I put up is just like a very short video. Like he has lectures where he talks about an hour and a half on this similar thing. But it's a very interesting hook. About how
and one of his
can be explained.
And one of the people listening in actually considered that there's this second process that's happening in evolution known as complexification, and complexification is also is not time symmetrical. So he was considering that possibly that complexification might also be under the second law as well.
Yeah, and the interesting thing to me, like where that ties into the property of emergence, is that you will get people like true empiricism will say all the time, like, look, you can't look at DNA and explain that through the laws of chemistry. You can't look at a gene from the laws of chemistry and say, therefore, bats grow wings. And what Alex Rosenberg and other people are trying to say is, you can't from a reductionist point of view. It is very, very difficult from a reductionist point of view to say this is going to happen. But if you step back and look at it from a different point of view, that you have very simple building blocks, very, very simple building blocks. And these building blocks undergo very, very simple rules, which are how they sort of relate to each other. If you propagate these things over time, we know they produce very complex structures. And now we're beginning to understand what the relationship between them have to be in order for the structures to become complex. If the laws are of a different type, you don't get complexity reside. You just get either very simple repetitions or they simply die out. So we're starting to learn this stuff now. So yes, it is essentially chemistry, but we're starting to see it's the chemistry of groups of things, not the chemistry of a thing. That's kind of hard for people to sort of
Well,
understand,
and
like from a molecule perspective.
Rosenberg went even one step further and actually says that evolution is actually not seated in chemistry. It actually is seated in physics, and that there are certain examples of physical objects that show signs of evolution. One of the most common examples used in that is oily vacuoles, little sacks of oils, and where they compete and they eat each other and they mutate and that kind of stuff. So I think that that's very true, and that's something that was very intuitive for me, but something that I never explicitly expressed, because I think that trying to describe the evolution in biological terms fell apart a long time ago. So they try to explain it in terms of chemical terms because they saw chemical processes that exhibited evolution. But now as the research has gone further, we're even failing to explain evolution in terms of chemical terms, and we're having to step back and even now try to explain it in terms of physical terms, and this is why I think that lecture you posted is so insightful.
Okay, it sounds though like you're saying everything eventually reduces to physics.
I agree. I'm kind of a reductionist. Maybe this course might change my view.
I'm hoping that I can get out of my reductionist frame. But I don't know. So far, seems like reductionism is the way to go, even granting the sort of compatibility of the two, and that you can step back and look at whole systems. But nonetheless, it just seems to me, at least thus far, that to get a good definition or whatever, you take the reductionist approach. And that seems to me to be some kind of a preference in the scientific community for a reductionist approach in order to ground your epistemology.
It's called bias. Okay, I have a question from the audience. Hello?
No one's watching.
Well, how exactly does biology fail to explain evolution?
Okay. So can you explain evolution in terms of biological terms? Things like
what kind of explanation do you
selection.
want?
Okay. Can you explain selection in terms of biology?
I think biology can do a pretty good job, explaining evolution. It depends on how you want it explained.
No. But okay. So here's a really good way to put it. How do you get evolution before there was biology? You kind of need biology to have evolution, and actually that's been shown to be false, right? So you can have evolution in in non-biological systems. If you were going to say that evolution is solely the purview of biology, you would need to show that you can't have evolution without biology.
Okay, in that case, yes, you could say that biology fails to explain evolution, but in the general sense, I don't think you can say
I'm not exactly saying that. I'm saying that you can't describe evolution in its most general sense using biological terms.
I really vehemently disagree with that.
Oh, okay.
And I don't like the idea of lending the word evolution to non-biological things, right? Because what about the classic definition? Change in allele frequency over time in a population.
Well, I agree, but what about things like genetic algorithms? Those are non-biological systems that evolve.
I agree, Isis. I agree. Evolution is just something simple through time, developing complexity. That's evolution.
Well, not just complexity,
so
but
if something
also
evolves more
conforming.
simply because of time, you can't call it evolution?
No. I actually disagree with Bunto there. I would actually say that evolution is the process in which a population molds itself to the environment. It becomes more fit to the environment. And so that doesn't. So that could be a series of chemicals, right? Where boiling, like you could even call distillation maybe even a form of fitness training, where the molecules that are being distilled off are not fit for that environment anymore. They get blown off and into the other flask.
Okay, the
That's
general
a form. Wait. That wouldn't be a form of evolution. That would be a form of selection, by the way.
right.
So, yeah, well, I understand that would be selection. So you know, I have the, I guess, a sort of a moral objection, right? What about? I guess I'm going to be conservative, right? What about changing allele frequency in a population over time? I think that's a great definition for evolution, and
Okay.
it would
Biological evolution, I agree, but there's multiple. Like I said, there's non-biological forms of evolution that have.
Well, but if that's the definition of evolution, then what do you mean?
Okay, just the problem is saying that biological evolution is a change in allele frequencies is like saying, okay, I have a theory of motion. My theory of motion is that sometimes things move and sometimes that they don't. Okay, that's kind of obvious. What the hell does that allow you to do? If you say biological evolution is a change in allele frequencies over time, you've given me a word that describes a phenomena. It has no working potential. It can't predict anything. It can't explain anything. In the same way, if I say I have a theory of motion, sometimes things move and sometimes they don't. It doesn't explain anything. Neither does that phrase, which people are sort of saying over G+, which drives me mental. It doesn't explain anything. It doesn't have any
It doesn't
predictability.
have
Well, what was wrong with
Hold
my
on. I got a big objection here, because this reminds me, and you guys can tell me where I'm wrong if I'm wrong, but this reminds me of the philosopher's objection to me complaining about justified true belief. Now, give me a second, and I'll explain how come. So when I talk about I don't like justified true belief as a definition for knowledge, it has to do with this business about it's sort of impractical and similar arguments to the ones that you're making towards evolution. So I could adopt the counter arguments that I get with respect to evolution, namely, look, I'm just describing it. It's just a description. To say change in allele frequency over time is merely a description. I'm not saying that we have to use it for application, or that this is related to how we came to know what evolution is, or that I'm describing sort of the process itself or anything like that. This is just a description so that we can have a description connected to the noise that sounds like evolution.
Fair enough.
And so that
Right.
that description isn't meant to, nor does it need to, be predictive in and of
Okay, so
itself.
I would
Fair enough.
agree. Okay, you've described the process. Now, so my next question would be, okay, fine. What is the explanation? How do we understand what's going on? How can we predict things? That's what I'd
Well-
ask you for.
Yeah, I
We're going
agree
that
with you.
direction.
What's the theory? What's the theory, right? You've given me you've given me what the term means. Like,
Right.
I can tell you, what is motion? Motion is the movement of an object. When an object is not motion, it undergoes zero motion. Okay, that's a definition of motion. But that's
Yeah.
not a theory of motion. Newton
No,
had
but
a
it's a
theory
good
of motion.
description. It's a good
Right,
description.
Right, what's the theory of evolution then?
So then you get into environmental, change, and the environment having an effect on organisms on an
Sure.
individual level and stuff like that, right?
Right, but that's not a theory.
Oh,
You want some sort of applicability towards the theory, right? That it can do a predictive. If we put, something single cell in an environment A, then we're going to get this outcome, right, Cliff? That's what you'd like.
Well, what is a scientific theory in general?
Well,
Like,
just to make it easy on you guys, there is none yet. There's multiple hypotheses. So, we have Lamarckian evolution, we have Darwinian evolution. It seems that both of them happen in certain circumstances, but we don't really have, we don't even have a proper definition of life.
Right, but you cannot deny it doesn't exist.
There's certain definitions of life, like something that grows, right? Crystals grow, right? Any kind of definition you have for life, I will be able to pick it apart at its seams and show you that there are things that we do not consider to be life that do fit your definition.
But the thing is that biologists never say that this thing does not exist, because that's why they come
Of
forth.
course not. Of course not.
no, but it's still not even about existence. But it's interesting because I agree, I really do, I don't think evolution is that great of a predictive model. I don't think it predicts much, right?
Hmm.
Because in order to make evolution predict things, you've got to control all of the environmental factors. Then, okay, you can make predictions. So I am sympathetic towards even creationists when they complain that evolution as a theory is not that great because it
Right.
doesn't predict very much.
I
That's
think
a
we can
valid
predict
criticism by the creationists. Yeah.
we can predict mutations. I mean, if we, some creature that we expose to radiation, they're going to have mutations. We can predict that.
Oh, you can't predict at what point. You can predict the
That it
percentage.
will occur.
Dose dependency. You can predict the dose dependency, but you can't
Sure,
predict.
but it's still something we can predict. We can say, well, if you expose this creature to so much radiation, you're going to have a mutation in its offspring.
Sure. I mean, but you're predicting the dose dependency. You're not actually predicting the exact point mutations that are going to happen.
Well, you have to take
What's-
care now, right? Like prediction in physics never is guaranteed. It never has to be, well, like I have to know exactly at time t it's going to be at x, y, z.
Thank you,
I mean,
Cliff.
like for example, it can be probabilistic, it can be complex, it can be many things. So when people say I can predict a behavior, in general, all that means is out of the total subset of things that could possibly happen, I can narrow it down probabilistically to a smaller subset. Like, so I can predict if I roll a six-sided dice, over time, I'll get an equal number of ones, twos, threes, four, and five, and sixes, and maybe on like really rare occasions it'll stand on its edge or do something like that. So that's a prediction, but it's a very probabilistic prediction. So the thing that Alex Rosenberg is trying to do is he's a bit biased though. I don't really like this thing where people say it's not physics, it's chemistry. If you ask physicists, they say there is only physics. All the rest of it's applied physics. They're just fooling themselves by calling it different things.
And
You
the
can't do something.
mathematicians would say that to physics. It's all
Yeah,
it's applied mathematics. Yeah.
Right. And
I agree with the physicists, to be honest.
But like I think
I
that's
do
all
too.
semantics. It doesn't matter to me. But what Alex Rosenberg is trying to do is bring a rigorous mathematical theoretical framework into biology. He's trying to say something like, look, there are real physical laws. If evolution is a physical thing, right? If Jesus is not involved in it, it has to obey real physical laws. Well, we know what the real physical laws are. The only physical law that can be involved here has to be the second law of thermodynamics because it's time asymmetric. What does the second law of thermodynamics say? And he's sketching out now what this actually looks like. So it's coming up with things like evolution has to produce local energy minima. If evolution didn't produce local energy minima, well then you wouldn't actually see constrained behavior. You would just see fluctuations. The only reason why things persist is because they are local energy minima. The other thing that it actually says is that it has to be extremely rare in events because that's what the second law actually says. So he's trying to build this rigorous mathematical framework into it, so you actually can make a theory of evolution, which is like Newton's laws in that way. It's a theory. It's a mathematical framework. It is in every sense a theory.
Exactly, and then he went on to say that evolution is essentially the only type of force that could actually create these kind of rare low energy state assemblages.
Natural selection.
Yeah, or natural selection, right? Yeah, not evolution, natural selection. Yes, exactly.
So he's only been making this argument for a few years. Physicists have only sort of been looking at biology in this light for a few years. Self-organization
Exactly.
as a concept has only been around for a very short period of time. And I think we're in a very exciting period of time because a lot of these new techniques and a lot of very interesting perspectives are being focused on it. And to me, it reminds me of the explosion that happened when quantum mechanics
Exactly.
started being explored, and all of a sudden, all this stuff sort of started coming out of nowhere. But initially, when people were doing the math, a lot of people just said, that's all whack. It's very difficult to work with. I mean, like there was a point in time where the number of people who understood something like general relativity was you could count them on the fingers of one hand. It took quite some time before this to spread out and people really start seeing the implications of it. But now general relativity is used in computations all the time, and the same thing for quantum mechanics. Like we have systems now. A lot of the electronics that we use, it's based on quantum mechanical principles. Electron microscopes and stuff work off quantum mechanical
Cell
behavior.
phones. I have
Yeah,
a question for Asus. Asus, don't machines evolve?
What do you mean? What kind?
Please don't say yes.
I know. I mean, there, like I said, there are certain algorithms that evolve, but there aren't any machines that I know of. Currently that
Okay.
evolve.
The airplane.
Okay, no, actually, it was created.
Anyone? I think the airplane evolved.
No.
Evolved.
If
This
you
is
think,
why I
yeah.
want to say change in the frequency over time, so that I
Yeah.
can just say quantum.
No. Okay, maybe the concept. Okay, maybe the concept of what an airplane is evolved, but you never had like two
That's
airplanes
just
like
evolution.
getting giggity with it and then like popping out a new airplane, right?
Okay. Evolution is simply something simple evolving through time to something complex. That's all the evolution is.
I disagree with that.
Yeah,
Can't things evolve into becoming more simple?
That is
I don't
true.
like-
Yes, exactly.
So I don't like us being all loosey-goosey with the word evolution. I think there's enough trouble as it is.
Right.
So somebody convince me, what are the advantages of a loosey-goosey definition of evolution?
I'm not advocating for a Lucy. Gosh, I'm advocating for
What
a
is-
physics-based definition. That's probably as hardcore as you can get.
Okay, so I guess I've got two questions then. Number one, is this physical definition that you're looking for more loosey-goosey or not? And number two, if
Definitely not.
is
Definitely.
there a more loosey-goosey thing that I feel like I'm hearing? Like, for example, to allow someone to say that machines evolve, it seems to me you have to loosen up the definition of evolution.
I think that's a popular misconception. I think
Okay, so how is it misconceived?
that
Because
a machine
you're in a
can evolve.
preferred position as a biological entity.
No, because Bunto, you're mistaking.
Evolve.
Bunto, you're mistaking sense for reference, if you know what I mean. You're
No,
thinking.
no. What you're mistaken, you're in a privileged position of a biological entity. You have to.
All right, Bunto's full troll mode on is like just.
Okay.
All I gotta say is
I'll go Isaac Asimov.
Nobody's taking the privilege. I mean, the privilege is just ridiculous.
All right. I think we've gotten way off of the original topic of foams. I think this has been a lovely conversation. So we're gonna have an after talk with all of this. But I think that probably the broadcast part. I think we've satisfied what we've had to say, right?
That's hilarious because we didn't even talk about foam.
And that's what I was saying. We talked about evolution for probably 3/4
Well,
of
talk
it.
about the phone.
Well, there's not much to talk about. It is a pretty.
Are you kidding?
Well, okay, there is, but just what was? I mean, if you have anything to add, please let's go back to that topic. How about that?
Okay, so from the Corsica crap, right? They were trying to point out, look, we've got this fluid, foam, and we've got this solid sand. And microscopically, it's easy to say that sand is a solid and foam is a fluid. But macroscopically, when you pull back and look at it, it's not so easy. And so the question is, right, and the reason for that is that foam acts like a solid,
Right.
and sand acts like a fluid. So the ultimate question that this course is going to explore is there a fundamental principle that can explain this emergence, right? So that this fact, this surprising fact, that macroscopically foam acts like a solid and sand acts like a liquid or a fluid, right? That this surprising phenomenon can be explained, can be subsumed under an existing law, or do we need a new law, or is it even right to try to subsume behaviors under general principles?
I actually would say no, or because for the one thing is how could you write the equation for the emergence of intelligence? It's something that is so surprising given carbon, oxygen, and a couple of other things. Or if there was, if we were able to come up with some sort of equation to describe that, it would be as boring and as dry as E equals mc squared.
Well, I hope we find a boring, dry equation that.
I agree. I think so, but I think intuitively, I don't think we will, though. I think that it is something so fundamentally complex, and that we may be able to capture certain facets of it, like maybe an equation that will tell us if something's going to act like a liquid or a solid based on its constituents, but nothing as expressive as to describe the emergence of intelligence. Maybe I'm wrong. I hope I'm wrong.
Well, what's interesting to me about this discussion is that it leaves the door open to, postmodernism or at least pragmatics, right? So it's I'm not so sure that even as an empiricist, we want to disregard the point that the postmodernists were making so fast, right? I don't think that we should just go, they were so full of crap, or let's just say pragmatists as opposed to postmodernists, right? In that maybe it is better for us to leave it loose as it is and adopt perspectives as they best fit our goal. And maybe that's all we should strive for, and that this idea of, a theory of everything is just a silly remnant from the Enlightenment. Now, I think that this discussion...
no, I think you're conflating 2 points. Oh, if you're not done, sorry.
Well, no, I'm just saying that one thing I like about this course is that it does leave a little bit of open room there, so that I'm not so willing to slam the door on a pragmatic approach to things.
I agree, but I think that so something like the theory of everything, and I mean the physical, taking the 4 laws of physics, basically merging gravity with the other 3 laws that have already been unified. That I think is something that is within our reach. But when you talk about the law of everything for the emergence of life or something like that, I don't think that if we were to come up with the equation that merged all 4 of the fundamental forces of the universe, that wouldn't just all of a sudden pop out the law of why we're here or how evolution evolved. I think that we can have laws of everything for a specific domain, like the 4 forces. But I don't think that we'll have an overarching law that describes everything, because for something to be so general, it would almost be reduced to the point of meaninglessness, because you wouldn't be able to focus on the important aspects of what you're trying to describe. You're just trying to describe everything. So like the quote-unquote theory of everything, which is really just the unification of the 4 laws of the 4 forces of the universe, that's a hyper-specific law of everything, meaning it's I don't know, that's kind of oxymoronic to say that, but it fully encompasses a very limited domain, and I think that's what we should be searching for, is a general law that encompasses a very well-defined domain.
Well, but so what you're proposing is that there is an advantage to specifying your domain.
And reducing, reductionism, yeah.
Yeah, so but that would mean that there are various domains, and that a pragmatic approach is the best one. And so then what is the ultimate goal of science?
Understanding.
But you see what I mean, right?
Yes.
Yeah. So that's one thing that I'm liking about this course. If you extend it to as abstract of a place as you can, is it does sort of bring up this idea of, perspective, and whether or not it's a good goal to try to explain the various different domains in some way that they are all explained by that one thing, or is it maybe better to just screw that and split up your understanding to the particular domain that you're studying? And who's to say one is better than the other?
Right, and I think you need to have a little bit of both, because one really good example is astronomy. So right now, astronomy is highly segmented, right? There's certain astronomers that will focus on their entire life on just the infrared spectrum or just the ultraviolet spectrum, and so that is good for comprehensibility and those kind of things. But having these kind of cross-discipline work is also extremely important for kind of the overall picture of astronomy. So we need a little bit of both. And I think that goes right in turn with the pragmatist standpoint, right, or the compatibilist standpoint. But Bento, you're saying something?
Well, this thing about various domains, I mean, that's kind of tricky. I can understand it, in a practical application, but it's a way of hiding scrutiny from another domain, don't you think, Helena?
I don't know. I
What do you
mean,
mean?
intuitively, I would answer yes to you. Yes, it's hiding, right? It's just that really what's at bottom is there's something you don't yet understand. However, it's possible that actually it's not that there's something that we don't understand, it's that there's actually no real there, right?
Okay.
Right? And so either one, right? And so I don't know necessarily that the there is no there is as crazy as the Enlightenment movement wants to make it.
Okay, well, what I was thinking was, you remember Stephen Jay Gould, and then he said something about different magisteriums when they were talking about religion and science.
Yeah, I don't even care about that, but let's see.
But see what I mean? That's what I mean. It's at the level of,
Yes.
you can just claim it's a different domain. See, that's what I mean. So it's like, no.
Yeah, sorry to say, but Stephen Jay Gould was wrong on a lot of things, but...
Okay, but I mean,
I can see the point you're trying to make. The point you're trying to make is a valid point, right? Is that if you're going to go, well, it depends on the domain, it depends on how you want to look at it, and it depends on what your goal is, and that will determine which method you want to pick up. Well, if you're going to do that, then you have to agree to open yourself up to the religious magisteria. All right? That's kind of the point you're making.
Well, my point is that there is no religious magisterium. I mean, we're all in one domain called reality that is subject to scientific scrutiny.
Yeah, well, but I think that's a continuum fallacy, though.
Point of view. You're objecting, right?
Well, I think that's a bit of the continuum fallacy where, okay, there's 1 grain of sand, there's 2 grains of sand, but you never get to the point where it's a pile of sand, right?
Well, that's out there. But the thing is like this. Okay, an assertion is made, right?
Well, but wait. You've heard of the continuum fallacy, though, or another good example. There's
you might have heard of it as the heap problem.
Yeah, okay, maybe a better example of the continuum fallacy is the rainbow, right? There's yellow, there's green, there's blue, there's orange, and they kind of all slowly mix from one to the next. And you can never say that there is at one point yellow, because if you move over just slightly bit, it still looks kind of yellow. If you move over a little bit, it still kind of looks yellow, but eventually it does turn into green and then to blue. And so the fallacy is saying that there is no yellow, there is no green, right? That there is just the rainbow. And that sounds what you're saying, Bunto, is that there's no kind of difference between all of it. It's just the rainbow.
Well, all I'm saying is that I'm leery of things that don't want to subject themselves to scientific scrutiny.
Okay. There is no spoon.
If somebody comes up with a domain saying that the science isn't there yet, see what I mean? That sets off warning bells.
I don't know. I rely a lot on the science isn't there yet.
I agree.
Really? That,
I have faith.
Claim...
I have a faith that science will get there, right?
Oh, yay, scientism!
Yeah, and I admit it, right? I mean, in my darkest hour, that's my faith. That's where my faith is.
Right. Yeah.
What prevents the theoretical physicists from just sitting around making up shit that will forever stump science?
Oh, well, the experimental physicists.
Exactly. Mm-hmm.
Yeah, they're going to say, okay, let me take your theory and
some sort of testing.
Right, like a really good example. The Higgs boson was recently found, right? Supposedly, who knows? There was multiple theories of the universe that were Higgsless. Right, there's especially in particular the Technicolor theory. It didn't contain a Higgs boson, but basically explained the laws of the universe. That specific theory was wiped off the table because we supposedly found the Higgs boson.
Yeah, that was so cool.
Definitely. or okay, a Higgs-like object, right? So yeah, definitely. There's a lot of theories that are put out there, and only very few of them will actually be useful or descriptive enough for us to adopt.
Yeah. At what point does use trump accuracy, or I don't know? It seems as though we often go with use, And,
Fair
and
Helena, we acquire the
yeah.
information and then we use it. That's the way science works.
No, but that's not true. That's not exactly how
We
science
acquire the
works.
information and then we use it. It's not the other way
No.
around.
No, sometimes it's the other way around. The Higgs boson is a good example.
Okay, we first made the use and then got the information. Then how do we
Yeah.
realize what the use was?
How did we what?
Okay, first we get the information, then we find a way of using it. So how can we?
It's not always true.
then
That's just
get-
simply not always true. When you get people like Cliff, or I don't know, name a theoretical physicist. I don't know, name one from our.
Oleg Yefimenko, one of my
Okay.
favorites.
All right. So, and they'll posit a theory, right? And they, especially in physics, because those guys are crazy nerds, they'll just, okay, well, let's assume that theory, and here's a whole bunch of math, and oh look, this math explains this thing that we don't have an explanation for right now, right? And so it seems as though, pragmatically, if those mathematical answers are working, physics will just run with them until either a better theory comes along, or the experimentalists start demonstrating the stuff that they predicted, like with the Higgs boson, right? And so it's not really true that we always start with bits of evidence and build a theory from there. A lot of times it goes the other way around.
Exactly. Actually, mesons were predicted before they were discovered.
Okay. I have a hard time swallowing that because I think of let's go into the realm of like free market, economics. How do you sell somebody on use without the information of how it came about in the first place? I mean, how do you sell somebody on that?
I don't know. It might be different. It might be different with something like economics.
Yeah, it's not as hard of a science as physics.
No, but it's a practical science. It shows you that first we acquire some information, then we find the use. I don't think it's ever been the other way around.
No. Like I said, like if you look into the discovery of mesons, they were predicted before they were actually discovered.
Okay.
Just like with the Higgs, they knew that this kind of thing kind of had to exist to make it sense of what we have.
Can I make a call out to Cliff here? Cliff, are you there?
Oh, and Bunto, do you mind putting on headphones? You're echoing wildly.
Come on, Echo. Well, I just see if Cliff. I'll just defer right now to Cliff what his thoughts are.
No, but Bunto, you're echoing wildly. Do you mind putting on some headphones? Thank you. But yeah, Cliff, please.
Yeah, I'm here. What's up?
Are you serious? You're saying what's up?
Yeah, what was the question? You were discussing a whole bunch of stuff. What did you want? Like, he just said you defer to me on what? Like, what did you want me to address specifically?
Okay, Bunto, explain about the theory thing.
Okay, I'll try to do it real quick without headphones. Don't we acquire information and then put some use to it first, not the other way around?
Yeah, that was that question. I think what...
yeah, I agree with that.
I think basically you and Helena might be speaking past each other. I think maybe Helena is saying that we can do something without fully understanding exactly it is what the theory behind what we're doing.
Yeah, like
sometimes
fire.
the theory only comes later, but sometimes it becomes before. Sometimes it becomes before. Sometimes it only comes later. I think maybe that's what she's saying.
That's right. I'm just saying that it seems pretty evident that sometimes it comes later. So that this idea that first you have a piece of empirical evidence and then use comes is not always the case. I don't think that's true, and I think Higgs boson is an example of that. And that's the only example I have in my head right now because I'm not a physicist, even a little. Right?
Well, let's just think of something really simple, right? Like, for example, people knew that there was this concept of mechanical energy and that they used it to do stuff long before they really understood mechanical energy, like as any kind of thing, let alone the equations for it.
Like, fire.
Okay.
Fire is a perfect example of this.
Like, people knew that, like, if you had a coconut, I could drop a rock on it to sort of break the coconut. Right, so they're using things. Now there's equations that you can actually show all this. And because we have the equations, we can now think of other things that we can do because we have this. So sometimes, like, we can do things without ever really understanding it is what we're doing. But other times you have people like Einstein, nobody really thought to use faster than, or really, really fast speed and the effects of it because we never experienced it. Like Einstein had to put out these theories, and people said, like, well, if this is true, we should be able to do these things. Let's just see what happens if we do these things. And people are like, holy shit, we can actually do these things.
Okay, how about this? Is it possible to use something with the point of zero information? You have no information at all and use something.
Yeah, like you're not speaking of theories or laws. You're just speaking about being
Well,
awareness of something.
well, here, Bunto, this is a good example. Do you have any understanding of the protocols or the data layout that is used to transmit this video and audio to the whole world right now?
Not as much in depth, but I mean, I have some information there that came first before the use.
Sure, but I mean, you could be a 2-year-old, a relatively smart 2-year-old, and your parents could show you, okay, click this button, click this button, hey, now you're talking to the whole world.
Right, but you see, there's still some information that the 2-year-old gets before the use.
Yeah, like when he says information, he doesn't mean like he's just meaning that for example, the 2-year-old knows like that allows him to communicate with somebody, or even that's a device that does something on a basic level, right? Like I can or on a basic level that thing exists and I can interact with it, and if I interact with it, I'll get a
and I
treat.
guess that's more of an
I
innate
think
understanding.
that's what he's saying, right? Like he's not actually saying like you need a theory of gravity in order to use things that use gravity. You just sort of need to be aware that things fall and impact other things, and then you have to do stuff.
What I'm really trying to say there is that information is vital for any sort of scientific enterprise. You know, so yeah, you may knock the theorists for not having any applicability at the moment, but I mean, use comes afterwards. First we get the information, then the use comes.
Well, I mean, the degree of backsliding you've done now, Bunto, has caused me to agree with you.
Backslid? Okay. I thought I was just explaining myself.
That's as upset as I've ever seen Helena in a
No, but okay, this is why it's useful, okay? Like the religionist or the theist will pose something that has no use. Have you discovered that? I mean, it's information that has no use.
No,
That's the difference between science and
I don't
religion.
agree with you. I think that the stuff that they posit has plenty of use.
The Trinity. How can we utilize? How can I run my toaster on the Holy Spirit? How can I run my car on ghost power? How? How can we use it?
No, but no. I think more. Helena's probably talking about more like the logical consistency that some of these people.
I don't know. There's some kind of equivocation going on, but I'm not smart enough.
I'm a materialist.
I want that toaster, man.
I want to harness the Holy Spirit in order to, have it run.
Listen, when your toast shows you Jesus, then you know there is knowledge
Okay,
there.
but look, Cliff, is that a form of postmodernism where you supply all this information that has no use, much the same way that religion does?
I'm not sure I'd want to constrain science to saying that investigations have to produce practical output. The reason why...
Why not?
Okay, so the reason
Not
why...
necessarily, right?
Right,
That
so...
is shocking, Cliff. Keep
right,
going.
okay, just give me a second. Let me explain.
I want to find out why not. You know.
Right, so... one of my sort of personal heroes is Richard Feynman for a lot of reasons. Mainly because I read about him when I was really young and getting into science.
Oh my God, that's the exact same with me. It's my favorite book. My favorite book of all time.
Yeah.
Surely you're joking.
Right. And,
That's on my bookshelf. I still get to read it.
Oh my God, you have to read it. All right, anyway, I'm gonna shut up and let Cliff talk.
So he writes about this passage in his life where he got completely burnt out. Of course, he's recognized by this point as being an absolute genius, and he already had many of what he was doing has very strong applications, but he got burnt out, and he sort of lost him the desire to do science, and he just wasn't doing it anymore. And he's sitting in a cafeteria, and he looks over, and he sees a guy screwing around with a plate, and he notices the plate has a very sort of odd movement. And he starts doodling and writing, trying to figure out the equations of motions for the plate. And he suddenly realizes that's why he got into science in the first place, because he just wanted to sort of understand the world around him, and it was that exploration of him trying to figure out was why he got into science. That's where his passion was. And when that switched over to become like, here's a list of problems that you need to solve, because people are paying you to do them, it became more like work, and he didn't really want to do it anymore. And there was no application. Like, even if he had figured out the equations of motions for the plate, it wasn't like people were going to use it to do anything. It was
Hmm.
just it was just an
Dude,
application that he was doing.
dude. Okay. Okay. There's a Buddhist religion where they say all is illusion, right? I mean, it has no applicability. I mean, once you say that there's no substance to things, there's some utility in our reality that you can use it. I mean, yes, you may claim that, there's no applicability for the plate moving, but surely somebody else besides him would have found some sort of use for that. That's science, the basis of science. You discover how reality works and you use it.
Right, but like at that moment in time, say he discovers how that plate works, and he writes out, or here's the equations of motions for that. That never gets used anywhere. Like he just throws that napkin away, right? So it never gets applied to do anything. But the problem is like if you restrict science, and like there's another.
That's not restricting science. That's
But
like,
no, that's not restricting science exactly. What would be restricting science would be to say that you only work on things that have utility
yes.
once you find the answers to them. And I would never want to do that. Like he talks about one time too where he took this job, and I think he worked for his son. His son was doing a startup, so Feynman goes there to work for him. And after they have a meal when they're all going to cook spaghetti or whatever, and they knock a box off the counter, and the spaghetti lands and it breaks, and someone asks Feynman a question. He's like, why does it break like that? Like why does spaghetti break in a pattern? And he takes like the piece of spaghetti by both ends, and he sort of bends it, and it breaks into a whole bunch of pieces. And he's like, look, dude, you're a physicist. Why does this break like this? And Feynman and him sit down for the next few hours, systematically taking spaghetti and sort of breaking it under different curves. And Feynman is trying to figure out how to apply the physics to this. And he said he never does figure out like why it breaks in the pattern it actually breaks. But like, and even if he did, that would probably never go into, because he would never publish it, right? He would just forget about that and move on with his life. So that's what but like to him, that was part of science. It was the exploration. It was the fun. It was no different than like somebody who wants to paint the sunset because he wants to paint the sunset. He wanted to figure that out simply because he wanted to do it, not because there was any utility in doing it beyond the fact that he wanted to do it.
How about this, Cliff? Is there such a thing as actual information?
I would say, yeah, depending on like how you want to define information or something. I'm not sure what you would mean by that.
I mean, you're presented with information and non-information. You can make the discernment.
Whether a system had like, yeah, like say if you gave me a series of letters, is there information in them or not?
And there's noise, right?
Yeah, sure.
Okay, but I mean, there is such a thing as actual information.
Right, yeah.
You can utilize actual information in science.
Yeah.
I rest my case.
Okay.
All right. So again, second time we got totally off topic. I'm loving it though. But all right, let's just tie this back up. Anything more about foams or?
I'm interested to see this idea of general laws. And number one, is it a good idea to look for them? And number two, if so, do we have a good one that would describe this phenomenon we all see, this surprising thing that we are calling emergence? So, and I think that the Corsica lectures are promising to touch on those issues, although they've now been promising to touch on them for 2 lectures. So I'm waiting to see if they really ever do.
One thing that I think we need to keep in mind is that some of these issues are very new. Like, not only do we not have general knowledge yet, we don't have fully agreement on what's going on. So, like, with the cornstarch one, there's one that'd be kind of difficult to do, but like it's done on colleges at time. It's not like the smartest thing to do, but where they decide, like they said, mix a little bit in a bowl, right? Well, if you get enough of like drunk sort of college people together, they can do it like in a swimming pool type area. You could make this thing in a swimming pool, and if you do make it in a swimming pool, you can actually run across it. It's not just like, but the thing is, if
Yes,
you
I've
stop,
seen
you
I've
sink
seen
down
video.
in, and it's
I've seen videos of
Right,
that.
and it's very difficult. You could easily get killed, right? If you make it deep
Oh yeah.
enough to ground, the pressure will crush you. So it's
Yeah.
not a sensible thing to do. But
Hmm.
people have made it on a small level because you can just make it like 6 inches deep, and you have someone around, and you know how to deal with it, who handles it, and people can run across it. And there's a number of people trying to figure out what's actually happening in the cornstarch, so that you don't just sink right down to it. And there's a couple of ideas, and one of them is that um, uh, when there's instantaneous pressure on it, because of that stress that's on the top layer, it forces a change in structure. You get a column of cornstarch underneath that pressure that becomes more like a solid than a liquid. But there's contention over whether or not that column goes all the way from the top to the bottom, and does it need to go all the way from the top to the bottom to actually suppress your foot from sinking down into it. So it's very difficult for us to have a theory of how this works when we don't even have a full set of observations yet. So we really need to get a lot more observations on this and say, oh yeah, it has to be a column. The column has to have this level of time domain. It has to have this spatial domain, blah, 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 blah. Now we can start to knit the theory together. Right now we don't even have enough observations to go beyond very simple things like it seems to be when things interfere with each other, interesting things can happen.
I like the last theory there. The last thing you put out. Right.
Right, and that's it's so general to almost be a truism, right?
Well, yeah, but it's so vague that it's beautiful.
It's true. It's true. I agree. Anyway, let me see. I think we've been going on for about almost an hour now. So maybe some last comments, and we'll tie this up for next week.
Very enjoyable.
Yeah, thank you all for coming. I'm really glad that got some regulars going on. So I'm sure I'll see you all next week. And to anybody who's gonna watch, thank you for watching. I guess that's it, if nobody objects.
Cool. I just wanted to say, like, next week is mainly on chaos. There's a bunch of
That's
videos,
gonna be-
lectures, and stuff
I'm excited
that
about that
I
one.
had sort of bookmarked that I'd sort of watch. I'm going to put up a few of them and just some short summaries. If anybody got any questions on that, I can deal with them in the comments after I put the video up. And you can also bring up any clarification points in discussion we have next week if you want me to address anything in the videos I put up.
Sounds great. I really love that you're adding extra videos. It makes it really, really way more interesting and deep. And, well, as you can see, allows plenty of tangents.
Yes, thank you so much, Cliff. You've been indispensable so far.
Cool. Okay, talk to you later, guys.
Later.